So it's a special delight of mine to introduce the next speaker. This is going to be Sandy Ryza from Clover Health. He and I previously worked together at Cloudera, where we talked a lot about big data with a lot of our customers. And so it was big data this, big data that. And so as retribution, he's going to come up here and tell us all about how he's now working at Clover Health to change healthcare operations with small data, which I think is also referred to as data. Okay, everyone, warm welcome to Sandy Ryza.
We actually like to call it artisanal data or small batch data. I didn't come up with that joke. So yeah, my name is Sandy. I used to be at Cloudera. I loved it there, but I also love it at Clover Health, where I am right now. I'm going to talk to you about driving healthcare operations with data science, which is kind of a mouthful. Our data is all small, as we talked about. We can get more into that later. When I describe Clover to my friends, I usually find myself using the words literally a health insurance company. So we're a small San Francisco tech startup. We're also literally a health insurance company. By that, we get fixed amounts of money per member per month. We have members. And then we pay most of their medical bills, modulo deductibles and copays, and all of that. So we had this word operations in our title, and I think maybe understanding that is the most important thing for understanding what this talk is about. What are operations in the context of health insurance? So on one side, we have insurance operations, and this is sort of like what you think of when you think of what an insurance company does. I guess if you think about what an insurance company does at all, I definitely did not before I came to Clover Health. But so, number one, this is approving and denying claims. So people say that they went to the doctor and they want money. And then, another big one is authorizations. So this is before a medical procedure happens. Providers will contact insurance companies to, make sure that they'll pay for it. And this includes sort of like maybe a broader sort of set of things that include catching fraud and all the various processes that surround these. And there's a lot of sort of interesting data work that can go into all of these. What Clover is really interested in focusing on, and I guess this box didn't really make it through the Google Slides to PowerPoint transition, but what Clover is really interested in focusing on, and what this talk is going to focus on as well, is clinical operations. So clinical operations is really the trying to make people a healthy side of healthcare. This is something that's sort of like the thesis of Clover is founded on the idea that this is really important. So we, sorry, is that a question? No. So we insure mostly seniors. Many seniors have chronic conditions, and like the vast majority of our of the money that we pay out comes from people who have chronic conditions, getting complications from those chronic conditions, and going to the hospital. So we think if we can control these chronic conditions and reduce the number of complications, people will go to the hospital less, and it really works out financially well for us. So what does this sort of come down to concretely? We call this closing member gaps in care. For most chronic conditions, it's sort of well known what needs to be done to control these and stay healthy, but it's really hard to get people to actually do these things. Many of our members are not taking their meds, they're not seeing their doctors, they're not getting screenings that they really care about. When we think about clinical operations at Clover, a big question is how do we get this guy, from Google stock photos to take his medications? We consider a bunch of different approaches we might take to try to make this happen. We can call people and tell them about the consequences of not taking their medications, hoping that this will scare them into taking them. We can ask members politely. We can look for our most non-adherent members, the ones that we know are not taking medications, and go, really focus all of our efforts on trying to get them to take their medications. We could try to segment, use different messages for members in different socioeconomic brackets. So in evaluating these decisions, this is where we come to the magical world, data science. If I had to pick monster from the Dungeons & Dragons monster manual to be the mascot for data science, I would go with the ogre. Ogres spend their lives living in really messy, filthy places, and sort of the main thing they do is walk around in the dark and hit stuff with blunt instruments. So I feel like that's at least a lot of what my life has been, both at Clover and at Cloudera. So when we think about data science, we think about answering a few different questions. First of all, what should we do? So what are these, this is what we were looking at on the slide before. What are the interventions that we think are going to be the most effective in getting our members to close these gaps in care? Something that sort of comes before this is like, what gaps in care do we think are most important to close? Then how do we target those? For whom? So who do we think is most likely to not take care of themselves? This isn't necessarily as simple as looking at who is, the most unhealthy, because it might be that somebody sort of has an advanced stage of a chronic condition, but is going to be likely to go to the doctor, and it's probably members that might be, less likely to, take care of their own health that we should be spending our time on. So that's the for whom. Can we predict who's not gonna, who's going to be unhealthy, who's going to suffer these bad outcomes? And then last of all, did it work? And this is maybe the most important one. How can we measure the success of any sort of intervention that we do to try to get people to be healthier? And understand whether it's worth it to keep doing it. Cool. So this is sort of general and high level, which is interesting and fun. But I think it's useful to be concrete. And so for the rest of this talk, I'm going to be discussing a particular thing that we did recently at Clover within the domain of data science for healthcare clinical operations. And so the question was, who do we call for home visits? We have a home visit program, and home visits mean we send nurse practitioners to the homes of our members, and the idea is that they can look through their medications, they can do some basic tests and screening, and we can try to first of all perhaps close some gaps in care on the spot. We can find conditions that we didn't know they had, diagnose them with those conditions, and then we can get them on track for maybe more complicated gaps in care that are difficult to close, that might require them actually going to a MD. So we were interested in sort of figuring out, so we have this call queue, and the call queue determines who we're going to call to try to schedule a home visit with. And so how do we order that call queue? How do we figure out sort of who is most in need of one of these home visits? For this particular project, we decided to focus on diabetes. About 1/3 of our members have diabetes, and this puts them at risk for a bunch of really nasty complications. For example, there's diabetic nephropathy, which is kidney damage that comes as a result of diabetes. There's diabetic retinopathy, which can make you go blind. Here we go. Yeah, so we wanted to understand sort of which of our diabetic members were likely to suffer these complications so that we could go diagnose them and get them on track for being healthier. To formalize this a little bit, can we predict which of our diabetic members will have complications in the next 6 months? So we've taken this really sort of complicated issue of diabetes and forced it in this really blunt binary classification model. On our feature side, we have every moment up until now, and basically everything that we can figure out about a member, all the information that we've gathered up to this point. So because we're a health insurance company, a lot of information sort of flows into us just as a basic prerequisite for us doing our basic insurance ops functions. So whenever someone has any sort of medical procedure, a claim comes to us, and that tells us sort of what diagnoses inspired that procedure, what's happened to them. We get all of their lab tests, so anytime they get some sort of like blood measurement, that comes to us. Anytime they fill a prescription and want to use their insurance to help pay for that, that comes to us, so we know what medications they're taking. And there's sort of like a host of basic demographic info that we get when they enroll. So that's sort of our feature space. And then on the label side, in terms of what we're trying to predict, did, in the next 6 months, were they diagnosed with some sort of complication of diabetes? To be a little bit more specific about the features that we ended up throwing into the model, I think we used 14 features in total. A few of the sort of most useful ones, we'll get a little bit into that later, were age. We thought older people might be more at risk for complications because health deteriorates with age. Comorbidities, so what diagnoses do they already have? Maybe these aren't diabetes complication diagnoses, but they're things that are related. So hypertension is a condition that's related to diabetes. Lab measurements like their HbA1c values, this is also known as glycated hemoglobin. Sort of the basic criteria for being considered diabetic depends on this lab measurement. So the higher it is, the sort of worse your health is, very bluntly. Yeah, so the idea was sort of, can we take all these features, can we take these labels that we have for our members, throw it all into a binary classification model, and hopefully get some good results. We face some sort of classic challenges that you come against when dealing with this kind of stuff. There was pretty high class imbalance. So even though diabetes complications are really terrible and they cost us a lot of money, only about 8% of our diabetic members end up diagnosed with a complication over a 6-month period. So of all the members we have with diabetes, it's actually somewhat rare to end up with these complications. So this means it's easy to get a model that has pretty high accuracy. We can just say everybody's not going to get any diabetes complications, and we'll be at 92% accuracy. But this doesn't really mean that the things that we care about, like precision and recall, are well optimized. And then let's skip that slide, it's kind of boring. Another big challenge that sort of shows up all the time, and this is like getting into Ogreland, is that healthcare data is really terrible. So missing data is huge. And in particular, one of the features that we wanted to use in our model, glycated hemoglobin, was missing almost 40% of the time. So we have all these members, we have these lab measurements for 60% of them, and 40% we just have not received any measurements in any reasonable time frame looking backwards. This is bad because it's clearly a very important feature. It's used in the definition of diabetes itself, and sort of various data exploration showed that it was really important. And it's also pretty tough because there's definitely it's not random who we're missing these measurements for. So if you're getting a measurement, that means one of two things. Either you're proactive about taking care of your health, which is a positive indicator for you being less likely to suffer complications, or you went to the doctor and they saw something scary and they were like, you should get this tested. So that would be a negative indicator. So there's definitely some selection bias in this population here, and we can't just drop all of the people that we don't have measurements for, because it would really end up overfitting to this specific group of people who we happen to have measurements. How did we end up addressing this? So we couldn't just throw out the feature. We couldn't just take out this column. We couldn't take out the rows because that would sort of bias what we're doing. And various complicated data imputation strategies didn't end up working. What we did do is simply hard code all the missing values to something that's outside the measurement range. So this is really terrible if you're trying to fit something like a linear model. But if you're using a tree, decision tree or tree ensemble model, which ended up being sort of optimal and other reasons, the model can basically split on have a measurement or do not have a measurement. So this nasty thing of trying to deal with selection bias and sort of this not random nature of who we're missing data for, the algorithm can sort of deal with in this blunt but somewhat usable way. And the important invariant here is that whatever selection biases are occurring here for this to work, for just hard coding these things as 0 and throwing it all into random forest, we need to hope those selection biases stay at play in future data, or they'll mess up our model performance. So this is something that sort of comes up in a thing that we're not talking about, which is monitoring model performance throughout time. Our final model ended up being a gradient boosting tree ensemble. it ended up doing sort of a lot worse than, let's say TensorFlow, MNIST models do, but a lot better than random chance. So these are sort of like our evaluation criteria. The area under the ROC curve ended up being 0.8. So for people who aren't that familiar with this metric for evaluating the performance of a classification model, 0.5 is sort of the worst thing you could get, and 1.0 is sort of the best thing you could get. So 0.8 is like respectable. There's some signal there. We ended up sort of picking a point such that the model would classify 25% of people as having complications. And given that threshold, the precision of the model was 24%, and the recall was 66%. 24% seems pretty low. Only about a quarter of the people that the model says have, will go on to get diabetes complications end up having diabetes complications. But if you look at the base rate, which is 8%, this is 3 times that amount. So the model is, when you take the 25% people who the model thinks are most likely to have diabetes complications, there's a 3x chance of those people having diabetes complications than this base rate. The most predictive features ended up being, nothing crazy here. The model is just sort of doing stuff in terms of how it combines these, but the most predictive features ended up being the glycated hemoglobin values, these lab tests, age, whether they had hypertension, and then whether or not they take insulin. So the last one makes sense. Insulin is a drug that you end up taking when no other drugs are really able to control your diabetes. So the fact that you're taking it means you're sort of more likely to get complications because the milder drugs that would control complications haven't really worked so far. So it's super nice that we have a scikit-learn Python object that is really good at predicting which of our members in the last 6 months ended up having diabetes complications. How is this useful to our business? Is this actually helpful? Knowing that you can get 24% precision and blah, 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 doesn't necessarily mean that this is useful in prioritizing our call queue. So we want to answer the question, do we catch more complications if we make calls actually using this model? And the most principled way of evaluating this is really to run a randomly controlled trial, to run an experiment. So here's the experimental setup that we ended up using for this kind of thing. And this is sort of different, or a little bit different than the standard controlled treatment experimental setup where you have a bunch of people, you split them into control, you split them into treatment, and you take some sort of intervention on all the treatment people and then compare all of them. In this case, the intervention was really about the prioritization itself. So it's not offer this service to this set of people, but this is the set of people that we think are, it's most important to offer this service to. So within the control group and within the treatment group, we created a subset, which was our call group. In the control group, this subset was chosen at random, so it was like 25% of the people in the control group. And for the treatment group, we chose those people as the people who the model thought were most likely to suffer complications from diabetes. The experiment is currently in progress, so I don't actually have results for you. If we did have results, these would be sort of like the nice results that we would expect, because I've crossed out the number there. But we got this matrix, whether they were in control or whether they're in treatment, whether we found complications when we actually sent a nurse to visit their home. Call them, schedule visit, send nurse to their home, search for complications. And we basically expect that in this treatment group, 3 times the number of people that we send nurses to their homes are going to end up with complications. So yeah, I think that's all I have for you. Thanks a lot.
So actually 2 questions. The first one is, did you ever use like unstructured data sources like medical notes and so on? And if you did, do you think they have been significant or, in terms of what you saw in the results? The second one is, why did you choose the 6-month window to predict, is it more of a medical reason, like at certain point in time, as of today, if someone does not have diabetes, would it take around 6 months for it to show up in the system, in the party system? Is that the reason? So.
Yeah, good questions. So for the unstructured data, the answer is no, we didn't try that at all. This was sort of like a 1-month project, so we wanted to like just pick the lowest hanging fruit off the data tree and use those first. My intuition is that if we were to look at charts and doctor's notes and all that, there would be a lot of stuff that would be predictive here. We haven't yet had the chance to delve into that. The 6 months was less of a medical thing and sort of more of an operational thing. 6 months gives us a wide enough interval to call these people, schedule all these different visits. So we have like 300 or so people who are actually in the experiment, and we didn't want to put a constrained time frame on how fast it would be to actually visit all of them and see what they had. Sweet. Thanks, everyone. Oh, what was that?
Hey, Sandy, how you doing? Ooh, God, that's loud. Sorry. Hey, so given all that you've learned about gradient-boosted trees and, hemoglobin and all that kind of stuff, do you think we should write a second edition of Advanced Analytics on Apache Spark? Is that a good idea? Should we do that?
Maybe advanced analytics with scikit-learn?
Ooh, wow, really? It's damn. Someone has given up the big data thing hard. All right, cool. Thank you, Sandy.